We can recall there is a wall. If the heat flow is in this direction, let us say the heat flow is Q. The direction of the heat flow is shown, and in this surface, let us say the temperature is T1. Let us say in this surface, temperature is T2. Alright, now again let us say the thickness is dx. The thickness of the wall being dx. So, from Fourier law of heat conduction, Q is equal to minus K A, or let us set the temperature difference T1 minus T2 is dt. K is dt by dx. A is the cross-sectional area perpendicular to the heat flow. So let us say this area is A. So the unit is what? So from that equation, if we neglect the minus sign, minus is nothing but direction of heat flow. That is, heat is flowing from the upper temperature to lower temperature. Minus sign is for that only. So K is equal to Q by A into dx by dt. So unit of Q is what? It is meter square. Dx is meter and dt is degree Kelvin. So that unit will become watt per meter degree Kelvin. The unit for K. Now let us go to the numerical. Here is the numerical on thermal conduction. Now, the inside and outside surface temperatures of a glass window are 20 degrees centigrade and minus 20 degrees centigrade respectively. If the cross-sectional area is being given 60 centimeter into 30 centimeter with 18 mm thickness. So the thickness dx is 18 mm. Determine the heat loss through the glass. Take the heat loss through the glass. Take the thermal conductivity, that is K, for the window glass as 0.78 watt per meter degree Kelvin. Okay, so let us first make a rough sketch of it. So that one phase, T1 is 20 degrees centigrade, T2 is minus 20 degrees centigrade, and area is 60 into 30 centimeter. So if we convert that into meter, it will become 0.18 meter square. Okay. Okay, so the cross-sectional area is given 60 centimeter into 30 centimeters. So 60 into 30 is 1,800 centimeters square. So convert this to meter square, it will become 0.18 meter square. So now the heat transfer rate is Q is equal to, let us write the formula first. Q is equal to K T1 minus T2 divided by length. So K is given 0.78, it is multiplied by 0.18 and again multiplied by 20 plus 20 and length is 18 mm. Convert that 18 mm length to meter, so it will become 0.018 meter. So ultimately the answer comes as, let me check whether it is correct or not, 0.78 into 0.18 into 40 divided by 0.018, 312. So the answer is 312 watt. Now the heat loss. Q is equal to Q dot to del T. So Q dot comes as 312 watt into 3 into 3600 second. So that will become 3.37 into 10 to the power 6 watt or megawatt. If we convert this into megawatt, then 3.37 megawatt. Then is the time. As it is said in the problem, that determine the heat loss through the glass cover in 3 hours. So convert that 3 hours into seconds. So 3 hours is converted into seconds by multiplying it with 3600. So by doing that, our answer will become 3.37 megawatt. That is the answer. Okay. Now, let me go to the convection problem now. Let us again recapitulate what a convection is. This is the conduction. Now the convection, we know. Let us consider a plate again. And here there will be fluid flow. So a fluid flow will be there. Now, let us say the temperature of the solid surface is Ts and temperature of the fluid flow, of the flowing fluid is T of fluid, and temperature of solid, where temperature of solid is always greater than temperature of fluid. Here is also minus K is only valid for T1 greater than T2. Otherwise, minus will not be valid. Here is also, we will develop the formula by fulfilling the condition Ts is greater than Tf. So from Newton's law of cooling, for convection, Q is equal to H A cross-sectional area, that cross-sectional area, let us say A, into surface temperature of solid minus temperature of fluid. That is the Newton law of cooling. Its unit will be, unit of Q will be W. Now let us determine the unit of H. So from that equation, H will be equal to Q by A into Ts minus temperature of fluid. So unit of Q is watt. So watt per area is meter square, and the temperature difference is nothing but Kelvin. So unit will be watt per meter square Kelvin. Unit of K is watt per meter Kelvin, and unit of H is watt per meter square Kelvin. Okay, now let us go to the problem. Here is the problem for convection. Calculate the heat transfer by natural convection from an insulated steam pipe. Insulated steam pipe, 10 centimeter outside diameter and 15 meter length. 15 meter length is given, and the outside diameter is given 10 centimeter, 0.1 meter. If the average surface temperature of the pipe is 160 degrees centigrade, so that Ts is given as 160 degrees centigrade. The ambient air temperature is 40 degrees centigrade. You know, air or liquid both can be taken as fluid. So Tf can be 40 degrees centigrade, and average heat transfer coefficient is 8.4 watt per meter square degree centigrade. So that value is given. Let us come to that formula again here. So H is watt per meter square Kelvin. Okay, it is given as degree centigrade, no problem. But that formula will have to be applied. Q is equal to HA Ts minus T, Ts minus Tf. Okay, so pipe dimensions and surface temperature. So known factors are pipe dimensions and surface temperature, air temperature, and convection coefficient H. Find heat losses Q dot W. So assumptions, obviously steady flow operating conditions, and 2, constant tube surface temperature. So the surface temperature remains constant always throughout the length of the pipe. In practical cases, it will obviously differ, but if we differ this, no problem can be solved. So it is wise to assume that the surface temperature does not change. The surface temperature remains always the same throughout the length of the pipe, and radiation heat loss is not taken into account. Some heat loss due to radiation must be there, but we will not consider that. H is given, temperature fluid is given, temperature solid is given. So let us directly come to the formula. HA Ts minus Ta for T infinity whatever. So here the area which comes into the contact of the fluid flow is ideal. So ideal has to be applied. So 8.4 into pi into D. D factor is diameter of the pipe. Diameter of the pipe is 10 centimeter. Convert this to meter, so 0.1 meter. And length of the pipe is 15 meter. So 15 meter. And the temperature difference 160 minus 40. So the answer will come as 4750 watt. 8.4 into pi into 0.1 into 15 into 160 minus 40. 4750 watt. So here is the answer. Okay, so convection problem is also done. Now we will go to the radiation problem. Let us go to the radiation. Radiation. Radiation is transfer of heat by electromagnetic radiation arises due to temperature of the body. Radiation does not need any matter. Firstly, in radiation, we have learned already Wien's law. It states that wavelength corresponds to the maximum energies inversely proportional to the absolute temperature, and Kirchhoff's law is the emissivity of any body is particular temperature is numerically equal to the absorptivity for radiant energy. And Stephen Boltzmann's law said that emissive power EB of a black body is directly proportional to the fourth power of its absolute temperature. And if we consider two bodies of temperature T1 and T2, we have to add a set factor there. F sigma is a constant multiplied by T1 to the power 4 minus T2 to the power 4. So F, from that equation, F is the factor depending on the geometry and surface properties. That constant will become 1 when black surface is enclosed by other surface. F is equal to emissivity when non-black surface is enclosed by other surface. And sigma A is Stephen's Boltzmann constant. It has got a fixed value 5.67 Newton to the power minus 8 watt per meter square Kelvin to the power 4. And from that equation, if we solve that equation, let us go to the equation T1 to the power 4 minus T1 square to the power square and T2 to the power square square. So T1 square minus T2 square, T1 square plus T2 square. Again, T1 minus T2 into T1 plus T2. So T1 minus T2 divided by that factor. That factor will become the radiative heat transfer resistance. If we represent this in form of thermal radiation or resistance, then that factor will be the resistance, radiative thermal resistance. Now let us go to the problem. This is the problem for radiation. The following data was obtained in an experiment for determining the emissivity of a surface. Plate size 20 into 20 centimeter, heat coil input 50 watt, steady state temperature of the surface 85 degrees centigrade, ambient temperature 30 degrees centigrade, heat transfer coefficient 16 watt per meter square degree Kelvin. Stephen's Boltzmann constant is given 5.680 to 10 to the power minus 8 watt per meter square Kelvin to the power 4. Estimate the emissivity of the surface. So emissivity, we have to determine the emissivity of the surface. Yeah. Now that plate is given, H is given, fluid temperature 30 degrees centigrade given, solid surface temperature 85 degrees centigrade given, 20 centimeter, plate thickness 20 into 20 centimeter, and Q is also given 50 watt. Let's go to the problem again. Plate size 20 into 20 centimeter, heat coil input 50 watt, steady state temperature of the surface temperature 85 degree, ambient temperature fluid temperature 30 degree, heat transfer coefficient is 16 watt per meter square Kelvin. Stephen's Boltzmann constant is also given. Now go to the answer. Now emissivity will have to be obtained. Epsilon. H is given 16 watt per meter square degree Kelvin. Fluid temperature 30 degree centigrade, 20 centimeter to 20 centimeter the dimension, Ts 85 degree centigrade, and Q 50 watt. Again, some assumptions: steady state conditions, uniform heat transfer coefficient H, ambient temperature equals to the surroundings temperature, ambient temperature equals to the surroundings temperature. Now, rate of heat transfer by convection and radiation, Q by A per meter square. Q is given 50 watts, so 50 watt, so watt per meter square. Watt per meter square heat transfer rate and heat loss due to convection. H del T. Q convection by A, Q convection by A is equal to, so heat loss due to convection is equals to the Q convection by A. So it is now 16 H and temperature difference is 85 minus 30, so 880 watt per meter square. 16 multiplied by 85 minus 30, so it is equals to 880 watt per meter square. Now heat loss due to radiation, Q radiation by A, so it is equals to total heat loss 1250 minus 880. 880 is the heat loss due to convection. So if we subtract them, 370 watt per meter square, that is the rate of heat loss due to radiation. So rate of heat loss due to convection, total heat loss, rate of heat loss due to convection, and rate of heat loss due to radiation. And we again know that the radiative heat loss is equal to that shape factor into sigma into temperature to the power surface temperature to the power 4 minus fluid temperature to the power 4. The difference of surface temperature to the power 4 minus the fluid temperature to the power 4. Again, Q dot rad by A value is obtained. So we only unknown factor is emissivity, sigma. That factor. So sigma is equal to 370 divided by 5.665 Boltzmann constant. That's sigma, and the temperature differences that has been converted to the degree Kelvin. So emissivity is coming out as 0.813. It has got no unit. So again, let us go to the things we have learned: conduction, convection, and radiation. From my class note, I will share that. Okay, conduction, the surface will be there. I can share the white screen also, where I have drawn. Yeah. Conduction, a plate is there. Q, T1 surface temperature of that surface and T2 surface temperature of the second surface. So Q is equal to Ka minus the flow from the upper temperature, higher temperature to lower temperature. So minus Ka dt by dx. This is what, and unit of K is watt per meter degree Kelvin. K is Q. Let's omit the minus sign. Minus is only the vector sign which represents the direction of heat flow from higher to lower surface, higher to lower temperature. So Qia dx by dt. Q is watt, meter square, meter, degree Kelvin. So meter will cancel out. So watt per meter degree Kelvin. And for convection, fluid flow will be there. Surface temperature solid, let us say Ts, and fluid temperature Tf, where Ts is always greater than Tf. So Q, Newton's law of cooling is Q is equal to Ha, Ts minus Tf, unit is watt. And from that equation, H is equals to Q by A, Ts minus Tf. Unit is watt per meter square degree Kelvin. Minus K signifies the decreasing in direction along the direction of the heat flow. Thermal conductivity, thermal resistance we have also learned, dx by K for heat convection. Heat conduction, it is dx by K, thermal resistance, and convection is fluid flow required. And convective resistance is 1 by HA, and the radiation governed by Ohm's law, Conduction, and Stevens-Boltzmann law. This is the emissive power, shape factor, or it will become sigma. It is sigma, shape factor, or epsilon emissivity. The shape factor becomes emissivity from that formula. Resistance, radiative thermal resistance can be obtained. So here it ends my lecture.